Greetings, everybody. So the topic of today's video is an experimental application of chaos, which is surveillance using chaotic cameras. Now, let's explain this. This application is very relevant to exploration and surveillance of any given area. Now, traditionally, in deterministic techniques, let's say we have this sort of rectangular area, for example, and we have an autonomous agent, like a robot or a UAV, that wants to explore this area, or maybe wants to surveil this area. Let's say it's some sort of security area. Now, in classic deterministic approaches, which are, of course, very, very optimal, we are having some sort of optimal path, and the agent follows this path directly in order to cover all of this area and either explore it, as I said, or surveil it. So as you can see, you can have this sort of going zigzag motion or this circular motion where you little by little, but deterministically cover the whole area. Now, this is the classic approach, and of course, it is a very optimal approach. But alternatively, there is another technique that has been discussed in the literature, which is that of a chaotic motion. Okay, so the idea here is that we have to surveil this whole area, but the path that we follow is not a fixed path. As I have right here, I have an agent, and it goes back and forth, surveilling the whole ground, but it goes, along its path, which is a chaotic path. And by that, I mean that I have some sort of a chaotic system, and I'm feeding some sort of, how can I say this, some sort of navigation commands to the autonomous agent, and the agent follows this command. Okay, so the path here is unpredictable, it is chaotic. Of course, it is suboptimal compared to the previous case, but due to the fact that it is chaotic, it is very unpredictable. Okay. And of course, this is an experimental idea, but ideally, we want to have this applied to applications relevant to, surveillance or patrolling, where we may have adversaries. So we want to move in a way that it is unpredictable, so that an adversary cannot predict where we are going to move next. This also has to do with chaotic maneuvering, again, in the situation where some sort of agent is being tracked, so they want to move chaotically and unpredictably. But there are other applications that we can consider. For example, some of the earliest papers in this application of chaotic motion had to do with firefighting. So we may have some robot autonomous that, unpredictably and chaotically sprays around water. And of course, we may have some sort of classic robot that cleans a specific place. So let's say a room when you're away. So potentially we may have household applications as well. Okay. So in one of our recent papers, instead of having this chaotic motion, we thought of something else, relevant again to surveillance. So let's say we want to have some sort of camera that moves around and surveils a space. Okay. So our idea was this. Let's say we have a UAV, okay, an autonomous agent. But if I make the autonomous agent move chaotically, I may have and to spend up a lot of energy. So chaotic motion in a UAV is very inefficient. So alternative, what we thought is this. Okay, let's say we have a UAV and we have a camera attached to the UAV. And instead of moving the UAV chaotically, we will move the UAV deterministically. But the camera that is attached to the UAV will itself move chaotically. So the idea is this. Instead of having this camera look, for example, at a fixed position, let's say that the camera looks directly down from the UAV, which is this sort of A footprint, we are going to have the UAV move chaotically. So what we do is we are controlling, as you see right here, the vertical angle, theta, okay? So how the camera moves up and down, and also the horizontal angle phi, if you like in English. So we are controlling this motion as well. So these two angles are controlled chaotically by using a very, very, lightweight chaotic system. And this way, the camera has an unpredictable footprint. So the UAV moves deterministically, it saves a lot of energy, but the camera attached to the UAV moves around chaotically. And this idea of chaotic surveillance is actually based on chaotic area exploration, as I explained to you earlier. But we are trying to think of alternatives to have a more energy efficient chaotic surveillance, right? So, of course, this is very experimental, but we can have some very, very simple simulations in MATLAB. I have actually provided the code below in the description of the video. So, this is a graphical representation. Instead of the UAV moves in both situations in a fixed coordinate, but in the deterministic case, we only take photos or videos of the exact area below the UAV, while in the chaotic case, the camera moves around and provides us some sort of chaotic surveillance of the given area. Of course, we can combine this with multiple agents. And let's say I have one agent that moves deterministically and another agent that moves with a chaotic camera. Okay, so possibly we could have a combination of determinism and chaoticity. Okay, to have some sort of optimal situation where any sort of adversary will have no idea how we're going to move next. So I have some simple MATLAB simulations. The code is in the description. So as you see right here, the line here, the fixed line, is the motion of the UAV, which is fixed, deterministic, and optimal, right? The green areas is the deterministic footprint. Okay, so in this situation, the camera is fixed and only looks directly under the UAV, right? Now, in the chaotic motion, though, we have this sort of chaotic footprint. So the blue areas right here represent the chaotic footprint of the camera, right? And you see, in some situations, this may be a bit suboptimal, but what we gain in maybe less area coverage, what we lose, I'm sorry, we gain in unpredictability. Okay, so again, against adversaries, this may be very, very, very beneficial. Okay, so this is the chaotic footprint. And as you see right here, we have the chaotic horizontal angle. Okay, so how the camera moves in the horizontal angle and how the camera moves in the vertical angle, right? In the vertical axis, I'm sorry. And of course, what we can also provide for both of these is some sort of threshold. So here, for example, for the vertical angle, I don't want to have the camera look very, very high up. I want to have some sort of constraint as to how many degrees it can balance around. Okay, so this is very easy to do because this simulation is very simple to implement in MATLAB code or in any language for that matter. So we can provide some threshold to control how much the UAV camera is going to strafe around, right? So this is easily doable. Let me provide you with many other simulations. So I have tried different constraints on the angles that are acceptable. So this is another example here of chaotic motion. Again, we have a much higher unpredictability. And again, we have this sort of chaotic strafing of the horizontal and vertical angles. And I think I have another situation here. Here I have, allowed much more vertical angle positions. So the UAV angle, camera angle strafes a lot harder, if you like, or a lot more freely. So this is why we have see this sort of much higher coverage and much more unpredictable coverage. So of course this is experimental, but I believe it is very easy to implement using a microcontroller. This is one of the things that our lab is very interested in doing next. But there is certainly a lot of papers published at the moment where they study similar problems. Okay, so the literature is rich, but we need to also consider implementations, right? So again, we have this sort of chaotic strafing in the angles. Again, another simulation where I have a lot more freedom for strafing for the chaotic camera. And of course, in all of these situations, you can consider many different scenarios. So here I said I had a scenario where the UAV moves, as you see, I'm sorry, in this horizontal straight line, but we can actually easily implement this in a static camera. So let's say I'm here in my room and right here on the corner of the room, I have a camera and this camera moves chaotically. Or let's say right above me, I have a camera and the camera is stable, it is fixed, but it moves chaotically. So this is a simulation that I have here. The camera in this room is right here on the, just above my head. And as you see, it moves chaotically all around, surveilling this area all around me. Let me also remove this line to have this more clearer simulation. So these are all the possible footprints, I'm sorry, all around me as the camera is above me and moves chaotically, you know. And again, I have a collection of unpredictable angles for the camera strafing. Okay. So as you see, there are a lot of simulations performed. The code is in the description. We are heavily interested in performing an implementation using microcontrollers. And there are a lot of papers that you can read on chaotic coverage and chaotic cameras. So I'm going to put a lot of papers in the description of the video. I strongly encourage you to go ahead and read them. Okay, they are very, very interesting. So very experimental, but I think it has a lot of potential. Any questions that you have, you can write them in the comments. Okay, so thank you very much.